Hello everyone, I am Paranjum from Sri Venkateshwara College of Engineering, Bangalore. The topic for today's presentation is Machine Learning and Deep Learning Approaches for Cybersecurity. Abstract. The rapid evolution and growth of the Internet through the last decades led to more concern about cyber attacks that are continuously increasing and changing. As a result, an effective intrusion detection system was required to protect data, and the discovery of artificial intelligence's subfields, machine learning and deep learning, was one of the most successful ways to address this problem. This paper reviewed intrusion detection systems and discussions what types of learning algorithms machine learning and deep learning are using to protect data from malicious behavior. It discusses recent machine learning and deep learning work with various network implementations, applications, algorithms, learning approaches, and datasets to develop an operational intrusion detection system. Introduction. The Internet is transforming jobs, learnings, and lifestyles, leading to the integration of social life and online activities, which increases security threats. Cybersecurity is essential for protecting data, networks, and systems from unauthorized access or modification, becoming crucial for businesses, governments, and individuals. The rise of the Internet and extensive data sharing has led to the emergence of big data, creating a need for advanced cybersecurity measures. Network security, a subset of cybersecurity, protects systems connected to a network from malicious activities, ensuring data security, integrity, and availability. Current cybersecurity research is focused on developing effective intrusion detection systems to identify both known and new cyber attacks with high accuracy and low false alarm rates. Overview of machine learning and deep learning in cybersecurity. Machine learning in cybersecurity utilizes algorithms to learn from data and make predictions or decisions. Enhances threat detection and response through pattern recognition. Its key techniques include supervised, unsupervised, semi-supervised, and reinforcement learning. Deep learning and in cybersecurity. Subfield of machine learning focuses on neural networks and complex data processing. Enables learning from unstructured data for improved accuracy in threat detection. Common deep learning algorithms include autoencoders, CNN, RNN, and LSTM. Advantages of deep learning. Handles complex problems with higher accuracy and lower false alarm rates. Superior in detecting sophisticated cyber threats and evolving attack patterns. Shift towards deep learning for more effective cybersecurity solutions. Intrusion Detection System. Intrusion detection is the process of monitoring network traffic and computer events to detect anomalies, often using software applications known as intrusion detection system, which help identify risks before security breaches occur. IDS can be categorized into network-based and host-based systems, with NIDS monitoring network packets and HIDS examining host computer events, while hybrid detection combines both approaches for enhanced security. Intrusion detection system approach. Detection techniques are classified into anomaly detection methods and misuse detection methods. Anomaly detection. This method assumes abnormal traffic is rare and distinct from regular traffic, using unsupervised and statistical learning algorithms to detect unknown or novel attacks. Misuse detection. This signature-based approach relies on known attack signatures, using supervised learning to detect and defend against familiar, suspicious, or illegal behaviors. Attack classification. As network grew more diverse, attacks became more sophisticated, leading to the identification of various types such as DOS, probe, U2R, worm, backdoor, R2L, and Trojan, each exploiting different vulnerabilities. Common attack methods include denial of service that disrupts network services, probe attacks that scan for open ports to exploit, remote to user for unauthorized access, worms that self-replicate across devices, and user to root attacks that seek root level access. Evaluation metrics. Intrusion detection system performance, whether using machine learning or deep learning, is evaluated using a confusion matrix with 4 key metrics: true positive, true negative, false positive, and false negatives. These metrics form the basis for performance assessment indicators. Accuracy measures a proportion of correct predictions with higher accuracy indicating better model performance. Recall assesses the model's ability to correctly identify all positive records. The F1 score combines precision and recall with higher values indicating a more effective model. Precision measures its ability to avoid false positives. The false positive rate represents the rate of normal records incorrectly labeled as attacks. Datasets. For effective intrusion detection system, the choice of datasets is crucial to ensure accuracy. As applications and networks grow rapidly, robust network security requires selecting appropriate datasets for training and testing the system. KDD CUP 1999 is the most widely used dataset for intrusion detection based on the DARPA dataset. It contains basic and high-level TCP connection data but excludes IP addresses and includes over 20 different types of attacks. UNSW IDS-15 is created by the Australian Centre for Cybersecurity in 2015, includes both normal and malicious traffic collected from real-world sources like Symantec, CVE, and Microsoft Security Bulletin. It features 9 attack families including worms, DOS, and fuzzers. CIC IDS 2017 was created by the Canadian Institute for Cybersecurity in 2017 and includes both normal and attack scenarios, simulating 25 users' behavior across protocols like SSH, HTTPS, HTTP, FTP, and email. NSL KDD is an improved version of the KDD dataset with reduced redundancy using KDD 99 attributes to classify attacks into DOS, U2R, R2L, and probe. PUIDS is a derivative of NSL-KDD, generating new synthetic instances based on the same format and attributes. Detection systems in recent works using machine learning and deep learning. Intrusion detection methodologies have evolved significantly to address ever-changing threats. Initially, machine learning was used for classification, but as performance demands increased, deep learning was adopted to achieve higher accuracy and lower false alarm rates. Machine learning IDS algorithms like SVM and random forest have been used for binary classification in IDS. SVM excelled in training while RF performed better during testing, with performance varying by datasets and features. Models using decision trees, naive Bayes, and RF demonstrated high accuracy, especially for detecting DOS attacks in the NSL-KDD dataset. Additionally, SVM was proposed for faster training and higher accuracy, though they may miss some features correlation. Artificial neural networks have been proposed for detecting malicious traffic by training on a diverse dataset of benign and malicious traffic. During training, ANNs adaptively tune their weights using a learning rule, resulting in an impressive accuracy of 98%, surpassing traditional signature-based detection methods. Deep learning IDS algorithm. Deep learning methods such as autoencoders, CNN, and RNN have been utilized for classification, with CNN and LSTM networks achieving the best performance, 91.8% accuracy for CNN classifiers and 90.1% for F measure. However, these models lack a crucial evaluation function as they treat all features equally. An intelligent intrusion detection system combining deep learning with network virtualization was developed to detect malicious behavior in IoT networks, achieving 95% precision and 97% recall across various attack scenarios, though it focused on detection rather than prevention. Another model using the NSL-KDD and KDD-CUP99 datasets employed a non-symmetric deep encoder to reduce training time and improve accuracy by 5% over pure autoencoders, though it struggled with complex attack detection due to its high false alarm rate. Research also explored CNNs with the NSL-KDD dataset, converting raw data into an image format to tackle class imbalance, which reduced the number of computing parameters but resulted in low accuracy compared to other models as seen in the figure. Challenges. The intrusion detection system field has many challenges represented. Unavailability of up-to-date dataset. An effective intrusion detection system requires continuous training and testing against both new and old threat datasets. Keeping the dataset current with diverse attack patterns is essential for improving the model's resistance to various attack types. Hyperparameter tuning. IDS models have multiple hyperparameters such as activation functions, optimization methods, the number of nodes per layer, and total layers that need specification. Proper tuning of these hyperparameters is crucial as it significantly impacts the model's accuracy and detection rate. Tuning can be done manually or through automated methods to enhance performance. Imbalanced dataset. Many existing datasets have an unequal distribution of records for different attack types, affecting detection rates. Attacks with fewer records tend to have lower detection rates. This issue can be addressed by balancing the dataset or increasing the number of records for minority attack types. Performance in real world. IDS models are often developed and tested in controlled laboratory environments using public datasets. However, these models must be validated in real-world scenarios to ensure their effectiveness and efficiency when deployed outside of the lab. Conclusion. Intrusion detection systems are a critical area of research in cybersecurity, focusing on safeguarding data from malicious activities. Current research explores new datasets and the integration of various learning algorithms. This work explains the concept of IDS, types of attacks, and how to evaluate the effectiveness of such systems. Additionally, recent research highlights various data protection implementation, initially using machine learning to identify algorithms that yield higher accuracy and lower false alarm rates. Extensive investigations have led to the conclusion that deep learning outperforms traditional machine learning by effectively addressing complex problems with improved accuracy and reduced false alarms. Previous studies have utilized diverse datasets, architectures, methodologies, and algorithms to enhance data security against attacks and threats. These are the references of the research paper. Thank you for watching the video.